Okay, welcome back. So today we're going to cover lecture 16, which is a continuation of rotational dynamics part 2. So let's think about what we've covered so far. We have talked about translational motion, and we've talked about rotational motion. Now with translational motion, we talked about position like x, y, and z, or the r vector position. And for rotational motion, we talked about the angular position theta. For translational motion, we have a velocity v. For rotational motion, we have an angular velocity omega. For translational motion, we have an acceleration a. For rotational motion, we had an angular acceleration alpha. All of these we could talk about the vector nature of those things, the directions. We basically thought about just one direction, either a positive or negative direction, but they are actually vector quantities too. We also have the quantity that causes an object to have a rotation, the force, and the analogous rotational quantity was the torque. So what other kinds of analogies do we have between translational motion and rotational motion? What else can we say? What other similarities are there between these different kinds of motion? Well, let's think about this. If we have an object and we know this object is not translating, it's not moving, we know the net force acting on it has to be 0. If it's not rotating, we know the net torque acting on it has to be 0. If we apply a torque, then we know the motion changes, it speeds up, we have an angular acceleration. But if there is no angular acceleration, we know we have no torque. But if we do have a net torque, what is the relationship between the net torque and the angular acceleration? Well, let's think about that. Let's imagine we have some mass m, and we apply a force to it. We know we're going to get an acceleration, and we know F equals ma. For the time being, let's just imagine we're talking about one-dimensional motion. We won't worry about the vector nature at the moment. Now let's see if we can figure out what kind of rotational motion this would have. How might this object rotate about some origin? Well, let's define an origin, and let's just put the origin over here, so that our r vector is perpendicular to F. That'll just make it a little bit easier to analyze. So what kind of torque do we have? Well, we know that the torque is equal to Rf sine theta. Now in this case, I've arranged it so that the force is perpendicular to r, so theta will be 90 degrees, sine of 90 is 1, so we'll just say that the torque is Rf. Now we know that this object is going to have an acceleration. It's going to have an acceleration in the same direction as the force, so I'll draw that, say, up here. So here's my acceleration. That's going to cause a rotational acceleration of the object. If you could imagine this was rotating around the origin, what kind of angular acceleration would it have? Well, we know that A is equal to R alpha, back from our rotational kinematics. So we've got these relationships. Let's see if we can take these and put them into F equals ma. What do we have? Well, we could divide both sides here by r, and we have F is equal to tau over r. Now let's take F and A and put it into this equation here. And what do we get? Well, we have F is equal to tau over r equals m times A, and A is R alpha. Let's multiply both sides by R, and we have tau equals mr squared times alpha. Now, this kind of looks a lot like F equals ma, where we have these analogous quantities, A and alpha. We have these analogous quantities, tau and F, but m in F equals ma is replaced by this mr squared quantity in the rotational form of Newton's second law. Well, what is that, mr squared? Well, that's actually what we call the moment of inertia. And we label that with a capital letter I. So we can actually rewrite Newton's second law in a rotational form. Tau equals I alpha. Now, what is this quantity I? We've talked about alpha, we've talked about tau. What is I? What is the moment of inertia? Well, let's think about Newton's second law. What is m in F equals ma? M tells us how difficult it is to accelerate something. So if we had an object, say a mass, the mass tells us how difficult it is to accelerate the object. If I wanted to push on this and accelerate it, the mass tells us how difficult it is to accelerate. How much force do I have to apply to get it to accelerate? In the relationship F equals ma, the bigger the mass, the more force I would have to apply to get the same acceleration. Or, for the same force, the bigger the mass, the less acceleration the object would have. So m, the mass, tells us how difficult it is for us to accelerate something. It's easier to accelerate something with a lower mass than it is for something with a larger mass. It's easier to accelerate this pen than it would be a great big boulder or something. It would be harder to accelerate. Let me get my pen. Now, what is I? Well, we can think about it in exactly the same way. I tells us how difficult it is to rotate something. How hard is it to get it spinning? For example, this wheel requires a certain amount of torque to get it spinning. This pen requires less torque to get it spinning. Why? Because this object has a lower moment of inertia. The smaller the moment of inertia, the easier it is to spin around, the easier it is to rotate. The higher the moment of inertia, the harder it is to rotate. Now, the moment of inertia depends on two things. Well, first of all, r, this is just the moment of inertia for one small mass. So a small mass, some distance r from the origin. Now, if we've got a more complicated system, like this wheel or this pen or something, the mathematical form for determining the moment of inertia is more complicated. But the basic idea is that the farther a mass is from the origin, the larger its moment of inertia. And if we have just a single point mass, the moment of inertia for that would be mr squared. The mass of the object times the distance from the origin squared. Now, this brings up an interesting problem. The moment of inertia depends on the distance the object is from the origin. In other words, it depends on where we choose the origin. In other words, if I were to choose the origin over here, that object would have a smaller moment of inertia. If I chose the origin over here, that object would have a larger moment of inertia. So the moment of inertia of an object is not just a constant quantity like the mass of an object. It doesn't matter where we put the origin for the mass of an object. The mass of this is still 5 kilograms, which is what the mass happens to be. It doesn't matter where we choose the origin. But the moment of inertia of an object, that depends on how we are trying to rotate it. For example, if I wanted to, let's say I want to rotate this mass, say around my central axis. In other words, I'm going to spin around like this. But I'm going to do it while holding this mass. If I hold it close to my axis, the r value is smaller and it's easier for me to spin around. But if I hold it far from my axis, oh good grief, it's actually much harder to spin around. So actually the moment of inertia of the object depends on how you try to rotate it. The farther from the axis it is, the larger its moment of inertia. So for some complicated object like the wheel or something like that, you have to determine, well first, how are you going to rotate it? Where's the origin? Now in this case, say the origin we might choose to be the axis. We're going to rotate the wheel around the axis. And then, how is that mass distributed? We can think about it that every little bit of mass of this wheel, wherever it is, has its own little moment of inertia that we could calculate, mr squared, from the axis. And then the total moment of inertia would be the sum of all of those little individual moments of inertia to give us the total moment of inertia of the wheel itself. Now, that typically takes some calculus to use to determine. We won't do that. I'll just tell you what some typical moments of inertia are. So first, and these are the sorts of things that are typically in a table in a textbook. So if you want to look up on some textbook, either the free textbook online or any textbook you want, typically there's a table that will list a number of moments of inertia. So some very common moments of inertia that we'll actually be using for a point mass of mass m, a distance r from the origin, has a moment of inertia of mr squared. For a hoop, now a hoop would be something like this. So basically a hollow cylinder where we are going to rotate it about the center. So we're going to put the origin at the center of the hoop. So imagine we're going to rotate the hoop like this, so about this axis, so kind of like a wheel. Because all of the mass is at the same distance, essentially, r from the center, the moment of inertia of a hoop about the central axis is still just mr squared. Now, what about a disk? And the difference between a disk and a hoop basically is a hollow cylinder, while a disk, we'll think of that as a solid cylinder. So the mass in the disk is spread out completely over the entire distance from the origin, and again we'll choose the axis of rotation to be the line through the center of the disk, so that'll be our axis. The mass is distributed all the way from a 0 radius all the way to a radius of, let's say, r. So in that case, again with our origin through the center, a total mass m of a disk of radius r, the moment of inertia is only 1/2 mr squared. And that's because a lot of the mass is actually concentrated at a smaller radius. And so the overall moment of inertia is less than for a hoop. And it actually turns out to be exactly 1/2. Now, we won't derive that, but those are some values that, we won't derive that factor of 1/2, but those are some values that will be very useful. One more, let me just mention, and that would be for a sphere. For a solid sphere of radius mass m and radius r, like this ball here, through any axis that passes through the center, the moment of inertia is actually 2/5 mr squared. And that's because even more than a disk, a lot of the mass, you can imagine like taking a disk and then pulling some of the mass in the front closer to the axis and pulling some of the mass in the back closer to the axis. Much more of the mass is even closer to the axis for a sphere than it is for a disk, and so the moment of inertia, 2/5, is even less than the factor of 1/2 for the disk. So those are just some different values for different moments of inertia that we'll be using later on. So what are the units of moment of inertia? Well, the units will be the units of mass, which are, what are the standard SI units? Kilograms. And the units of r, a distance, standard SI unit is a meter squared. So the standard SI units for moment of inertia will be a kilogram meter squared. And I'm sure you'll be glad to know there's not a separate unit that we'll use for that. We'll just leave it in terms of kilogram meter squared. Okay, let's stick some numbers in here. Let's imagine that we've got a uniform disc pulley. So maybe something like this. So here's our pulley that's held at the center. So it's free to rotate about the center like this. Now, around the pulley is a whole bunch of string, and we're pulling the string off from the top of the pulley with a force of 3 newtons. Now, the pulley starts off at rest. So initially, the pulley is at rest, and then we start pulling the string off. Let's imagine the pulley has a radius of 10 centimeters and a mass of 1.25 kilograms. Now, the questions are, What is alpha? What is the angular acceleration of the pulley? As the string is pulled off the pulley is going to start to rotate with some angular acceleration alpha. So what is that alpha? What's the angular acceleration? And then let's imagine we continue pulling this string for 2 seconds. The question is, how much has the pulley rotated after 2 seconds? In other words, what is theta after that 2 seconds? And then, how much string have we actually pulled off? What length of string have we pulled off in that 2 seconds as the pulley is rotating? So let's see if we can figure that out. Well, we're going to use the rotational form of Newton's second law. We have that tau equals I alpha. So if we can figure out the torque and we can figure out the moment of inertia, we can figure out what the angular acceleration is. So what's the moment of inertia? Well, we have that it is a uniform disk. We know the moment of inertia for a uniform disk is 1/2 mr squared. So 1/2 mr squared. In other words, 1/2 times 1.25 kilograms times 10, let's convert that to meters, so 0.100 meters, squared. We multiply that out, and we get that I is 6.25 times 10 to the minus 3 kilogram meters squared. Okay, so there's I. Now, what is the torque? Well, we'll look up here. We've got a force that's being applied onto the pulley, basically here where the string is coming off. F is going to be 3 newtons. We know the torque is RF sine theta, where R is the distance from the origin to the point where the force is applied. Now the origin is here, the point about which the pulley is rotating. R is then going to be that distance, the distance from the center of the pulley to the point where the force is applied, but that's just the radius of the pulley, 10 centimeters. F, that is 3 newtons. Theta, now remember, what does theta mean in this equation? Is it the theta that we're looking for over here? No, it's not. Remember, in this equation, theta means the angle between R and F. So if that's R, here's R, and here's F. What is the angle between R and F? Well, remember, we have to put them tail to tail. So here's F, here's R, we put them tail to tail. What's the angle between them? 90 degrees. So the torque, in this case, is R, 0.100 meters, times F, 3 newtons, sine 90 degrees. And I'm running out of room there. 90 degrees. What do we get? Sine of 90 is 1. We get 0.300 Newton meters. So the torque is 0.300 Newton meters. So what do we get? We get that alpha is equal to tau over I, which is, the torque is 0.300 Newton meters, divided by I, which is 6.25, times 10 to the negative 3, kilogram meters squared. We divide that out, and what do we get? We get 48.0. Work through these units, and what you'll get is inverse seconds squared. But remember, for an alpha, we're going to put that little unit of a radian in there, so that is radians per second squared. And there we go. There is alpha, 48 radians per second squared. Now, what is theta? Well, now it's a purely kinematic rotational problem, rotational kinematics. So, I'm going to get rid of the rest of this, and I'm just going to leave up alpha. We've got alpha equals 48 radians per second squared. How are we going to solve for theta? Well, remember the 4 rotational kinematic equations. We're going to use the third, where theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. We'll assume the initial angle is 0. So we'll assume that we're measuring any angles from the initial position when the wheel has not rotated, when the pulley has not started rotating. So we'll say that theta naught is 0. We assumed, or we were told, that the pulley was starting from rest, so omega naught is 0. So what do we get? All we get is that theta equals 1/2 alpha t squared. In other words, 1/2 times 48.0 radians per second squared times t, and t, remember, was 2 seconds. We multiply that out, and what do we find? We find that theta is equal to 96 radians. There we go. Now, what about that last question? How much string has been pulled off? Well, the length of string that has been pulled off is basically the distance around the wheel that the wheel is rotated as the string is pulling off, so that distance is the same as the arc length around the wheel. Well, we know the arc length, S, is equal to r theta, where r is the radius of the wheel, and we know that is 0.1 meters, so 0.100 meters times theta, which is 96 radians, and we get that that arc length, or the length of string that has to be pulled off, is 9.60 meters. And there we go. There's the answer. Very, very good. Okay, now, what other sorts of connections are there between rotational quantities and translational quantities? What about any of those other things that we've already talked about with translational motion? Is there, or are there, analogous quantities for rotational motion? Well, the answer is yes.